Thank you. It's wonderful to be here again and have this opportunity to talk to you. It's a bit of a strange title, and the reason for that is the James Webb Telescope has undoubtedly opened a new era in the discovery of life beyond the solar system. However, the initial excitement and promise has not quite lived up to our hopes and expectations. So what I'm doing tonight is taking a more broad view of the whole story of what we think about where there is life out there in the universe. So we have to start by saying, what is life? And I love this definition, a self-sustaining chemical system capable of Darwinian evolution. I love it for all the issues it does not address. But I think we can all look at it and have a good feeling that we do realize what that means, and it's not a bad definition. So having put that before you, let's now look at the broadest view that we have, and that is that we live in a universe that is perfectly suited to our existence. And what do I mean by this? I mean that the laws of nature and the values of the physical constants are perfectly chosen to allow life to develop. One example of that is the relative strength of gravity compared with the electromagnetic force. You'll see gravity is enormously weaker. If gravity was only slightly stronger, the universe would have all collapsed into a black hole. If it was only slightly weaker, the universe would have expanded and no stars or galaxies would have ever got together. So that's just one example. Why it should be? Maybe there's an as yet undiscovered super theory that naturally links all these constants, though that does not seem to be the way thinking physics is going. Maybe there are many universes, the many universe theory, so we naturally only occur in the universe perfectly suited to us, which just removes the mystery one stage further back. And maybe there was some supreme being who created the universe, which leaves us the problem of which universe that being exists in. But there we are. We live in this universe. This universe is full of galaxies, 100,000 million galaxies just in the observable part of the universe, and within each galaxy 100,000 million stars. And amongst those stars, when we look at a galaxy, a little detail of a galaxy, we see these dark regions, these regions where stars are being born, in the centers of what are called giant molecular clouds. And they're called giant molecular clouds because they're full of molecules. And you're not supposed to be able to read this table just to marvel at the number of entries, from diatomic molecules at one end up to molecules with 22 atoms or so in them. And these are all found in comets, in interstellar space, in giant molecular clouds. And amongst these are the fundamental building blocks of life. So there's a lot of stuff around. Okay, let's now move a little bit closer to home in our own solar system. And I'm sure you're all familiar with the concept of the habitable zone, the region in which water is a liquid. And of course, we realize that we need a solvent for chemical reactions to take place. And then that must lead us briefly to the next speculation as to what we mean by life. And clearly there is this hierarchy of life, and the percentages in red there show the time, the length of time so far on Earth that particular hierarchy or a form of life has existed. Now, today we're going to focus entirely on the single-celled organisms. It's quite another talk to talk about technologically advanced, something I think I've talked here before. And then taking the broad view that astronomers like to take, throwing everybody else's field into kind of just trivializing it in a way that is really rather inappropriate, but makes a point that this is the entire history of the Earth, the 4,500 million years, and you will see that the oldest known rocks are almost as old as the oldest traces of life. So that is one great mystery. But then the other point worth realizing is that for 1, 2, 3,000, more than 3,000 million years, there was essentially nothing on Earth except single-celled organisms. And so most of the time, this Earth has been inhabited by single-celled organisms. So maybe that's the most we can expect or hope to find elsewhere. And of course, the rest of it, everything multicelled in the last 600 million years or so. Now, the other point to make about life, which is a very kind of exciting and positive point to make about life, is that it is widespread and tenacious. And these images here all represent environments where life exists. In this Lake Mono, which has very high levels of arsenic, there are organisms. It was once thought that the arsenic had replaced the phosphorus in their DNA. That turned out not to be true. The cells are full of arsenic, but probably trying to find the phosphorus. In Antarctica, we find Colwellia, an organism that thrives at temperatures of -20 that is found to be living in ice cores that are 100,000 years old, that may even be viable at liquid nitrogen temperatures. We go to the centers of oceans and we find these smokers, these regions where water is emerging, temperatures above boiling point, rich in minerals, and we find this Pyrolobius fumari that lives there, thriving at 90 to 113 degrees, temperatures at which we normally sterilize. We find the hot springs colored in beautiful ways by these archaea. Most of these are called archaea, but they are also single-celled organisms. And perhaps, to my mind, one of the most extraordinary places has been the discovery of organisms living up to 2.8 kilometers below the surface in basalt rocks with no apparent contact with any photosynthetic material. And this Beatrix gold mine is 1.3 kilometers deep, and you see water that is 2,000 million years old emerging from the rocks, and it's full of hydrogen from the radioactive decay, and within that are organisms that are living. We're not claiming that they're that old, but this is certainly an environment far removed from any photosynthetic activity. So what you see is that life on Earth is extraordinarily tenacious, and if it's any consolation, whatever we do, if we destroy every animal, every blade of grass, there will still be all these organisms will be around. We may have set, evolution back 600 million years, but we can start again. Okay, so what about the rest of the solar system? Well, there was a lot of excitement in 2020, this is Venus, when phosphine was detected in the atmosphere of Venus. In fact, the first detection was immediately debunked, and all kinds of rather negative papers came out saying they'd got it all wrong, the calibration was wrong. But since then, the phosphine has been confirmed. And what is exciting about phosphine is, well, phosphorus is important for life on Earth, that phosphine is dissociated by ultraviolet light, and therefore, if there is phosphine in the atmosphere of Venus, it must be being continually made. And we do not know of a abiotic, that means a way of making phosphine. It doesn't mean there isn't one. Now, where is that phosphine? Well, it's certainly not on the surface of Venus. This is a Venera Russian satellite that landed in 1981, an extraordinary bit of technology because the temperature here is about 457 centigrade. The pressure is about 100 times atmospheric, and it's carbon dioxide. If you were there, it would be like wading through water. This thing survived for about an hour before it became defunct. So no life there. But maybe there was a time when Venus harbored life, and it has this very dense atmosphere, very strong greenhouse effect. But if we go up in through the atmosphere, we get to a point where the pressure in these dotted lines is about that in the Earth's atmosphere, 1 bar, and we find the temperatures are very like that on Earth. And it is hypothesized there might be, doesn't sound very exciting, but there might be some single-celled organisms, perhaps a residue of life that might have once existed on Venus, that can live here, that can form spores that fall and then are carried up, and there can be a kind of reproductive cycle going on within the atmosphere. And to that end, there are 3 missions planned to go to Venus. The first one, the Venus Life Finder, is supposed to go next year and will essentially, it's on the cheap, $10 million. It will do a sort of dive through the atmosphere, free fall, and measure parameters as it falls and goes through that area. Whereas Veritas and Da Vinci are 2 satellites that will do a lot of imaging and infrared and radar topography before also diving through the atmosphere. We hope that Da Vinci may get to the surface and take some images before it finally gives up. So there's a possibility of life. Now, when we come to Mars, we have for years seen evidence and been aware that water has flowed on Mars. This happened billions of years ago. There is water still on Mars, but it's locked up in the poles and beneath the surface. But when we look at the surface of Mars, we see evidence of sedimentary rocks. We see evidence of a time when there was certainly flowing water on Mars. One of the exciting things about Mars, we've known for some time, is there is a seasonal variation in methane. Methane is puffing up through the surface of Mars on a seasonal basis. Now, this could be a life sign, but the problem with methane is, apart from microbes as a possible source of methane, there are chemical processes, olivine interacting with water and carbon dioxide at temperature, that can also produce methane, and it's possible that methane can even arrive in the form of extraterrestrial material. So until we could get there or sample the methane and look at things like isotope ratios, that remains an open possibility. But one of the most exciting things, perhaps, discovered by Perseverance rover in this Jezero crater, a crater that was once filled with water, and you can see a fossilized delta there in the yellow box, where the river used to flow into this crater at the point of this arrow. Let us now zoom in on that. There we are in this dried out riverbed with some drifting sand there. And if we look over there, we're in this white rock here, which is being examined by Perseverance. And here is the Perseverance rover up against the junction of the white rocks. And this one in particular here has caught its attention, and the attention of the people using it. And what do we see? There's a red mudstone here. That's the reddish rock that is, as they describe, it does contain organic carbon. That's not meaning from an organism. That's just a description of its chemistry. And it contains a lot of ferric oxide, which gives it the red color. And you'll see these white veins of intrusive calcium sulfate with crystals of olivine. It's thought that these are intruded into this rock, and there's no evidence of life here that thought this material was intruded at much higher temperatures. But if we look at these peculiar features, the arrows point to little black dots called poppy seeds, and the circle encloses a leopard spot. And it's possible Perseverance has analyzed the chemistry of these things. It finds the dark poppy seeds are enriched in iron, phosphorus, and zinc, and this is similar to a mineral known as vivianite that is associated, found in bogs where the organisms live. And the leopard spots, a bleached area, possibly soluble in water, are enriched in sulfur, iron, nickel, and zinc. And on Earth, these are signatures of places where there has been some bacterial activity. So in a way, I think many people consider that this is the best evidence we have as a possibility for life. Samples have been taken. Until we get a sample return mission, we will not know the answer. One of the intriguing features we see on Mars are these two black things. They're actually holes in the ground. They're 100 meters or so in diameter and about 100 meters deep. You can see a bit of a hint of craters there. We see similar features on the Moon, and we see similar features on Earth in places like Hawaii, where there has been a flow of lava in a lava tunnel, and then the flow stops, the lava hardens, and bits of the tunnel collapse. And it is possible, by turning up the contrast, to look deep into these holes. As I said, they're about 100 meters across and about 100 meters deep, and radar imaging has shown that there is some tunnel underneath. What's exciting about this? These are deep enough to shield life from cosmic rays, which would now extinguish life, living organisms in the first meter or so of the surface. They're not only a possibility that there may be some residual organisms here, but they would certainly be a very good place if people like Mr. Musk go to Mars. That'll be a great place for him to live because it'll be safe there. So people going to Mars, this would be a good place to be. Okay, so Mars, certainly lots of potential. Even when we move out to Jupiter, we see a range of satellites of increasing distance and increasing geological activity. All the geological activity on these moons is created by the tidal effect, the gravitational pull of Jupiter. So we're now talking about potentials for life organized where the energy input comes from tidal forces. Perhaps the most promising one we've known for some time is Europa. And although the surface is minus 200 or so, when we look in detail at the surface, we see what look like broken ice flows. And this brown staining, which is now understood to be sodium chloride that's been irradiated by a high energy, gamma rays, X-rays, that sort of thing. And so it looks as though that every evidence suggests that what we are looking at are broken ice flows. These are some details at 1.7 kilometers, a mile from top to bottom. And these are regions where we think just below the surface, or maybe 20 kilometers below the surface, there is liquid water, a sea. And we've even seen, the Hubble Space Telescope saw some jets of gas emerging from Europa. Now, for that reason, there is the Europa Clipper mission, this was launched in 2024. It'll arrive at Jupiter in 2030. It will not be landing on the surface, but it will be sniffing the gas and doing all kinds of imaging, gravitational measurements, magnetic field measurements, and so on and so forth, to try and better understand the environment with the aim of looking for life. At the same time, there is a ESA, European Space Agency mission, and the new Astronomer Royal, Michel Doherty, is an important scientist, lead scientist on this project. This will do similar things. It will look at Europa, but it will also look at Ganymede and Callisto. And the great thing about Ganymede is that Ganymede still has a bit of a magnetic field, and where there's a magnetic field, there is thought to be a liquid core, got to be a liquid core. Where there's a liquid core, there's heat. that can give us smokers. And again, we believe that beneath the surface here, there is liquid water. So another candidate for life, and even Callisto, that we've considered essentially inert. When you look at the surface, you see this dusty regolith, as it's called, with these little bright, spiky mountains of water ice that is subliming, look like a completely inert world, but gravity measures and so on suggest again there's liquid water below the surface. That brings us on to our next and last port of call for potential life, Saturn. That's observed with the James Webb, rather beautiful image. And Saturn has this wonderful moon, Enceladus. And Enceladus is not that big. It's only 600 kilometers or so in diameter. And in fact, again, this is thanks to our astronomer royal, Michelle Doherty. With the Cassini spacecraft, she noticed these jets, or rather she detected plumes from their magnetic effect on the magnetic field, and then we observed these jets of water emerging from the South Pole, and I believe more recently some have been seen from the North Pole. It's not just water, it's CO2, a bit of nitrogen, a bit of carbon monoxide, a bit of methane, and a bit of acetylene coming out here. Where do these come out? They come out, some people have likened this major ridge to a sort of mid-Atlantic ridge where there might be some upwelling and separation. And just for comparison, I've put Europa, the structures on Europa that look very familiar at the same scale as those on Enceladus. Perhaps the most exciting object around Saturn is Titan. And you may well remember that when the Cassini spacecraft got to Titan, it dropped a probe, a Huygens probe, into the atmosphere. Titan has an atmosphere largely of nitrogen and methane, colored yellow apparently with acetylene. And there we see the glint of light from the northern hemisphere sea, and this sea that looks so familiar to us with the little rivers flowing into it, these windy rivers. This is a sea not of water, but of methane, and mainly methane and ethane, at a temperature of minus 180 degrees or so. The rocks here would be rocks of water ice. And so this gives us the potential for a whole different suite of life forms perhaps living in methane and ethane. And people speculated that if there were organisms living there, if they came back to Earth, they would spontaneously combust. But just to add to the extra mystery of Titan, below this ice crust with its sea floating on the surface, up to 40 or more meters deep where it's been measured, is again a layer of liquid water. So we even have liquid water on this particular object. So I think what we've discovered from our tour and of the solar system is that possible habitats for life are extended way out beyond the habitable zone and are deriving their energy not directly from the sun, but from other forces, from tidal forces. Now that brings us on to the next stage, which is to look at other planets around other stars, known as exoplanets. And we have been observing these probably for about 20 years now, and there are two crucial observations. And the first observation is to detect the motion of the planet. Now, we cannot observe, except in very, very few cases, the actual planet. So what we observe is the velocity, the movement of the star and the planet about the common center of gravity of the planet-star system. And what we observe is the Doppler shift, the blue shift and the red shift, and the period, of course, the time it takes to go around once. And clearly, it's much easier to observe massive planets but going around low-mass stars because the amplitude is much greater. And just to give you a feel for this, This is, that's the sun. The yellow thing is the sun to scale. And what you will see is that the way this has been depicted, it's kind of the other way around, is the movement of the center of gravity of the solar system with respect to the sun. Of course, in reality, the center of gravity, the barycenter, remains fixed in space, and the sun performs an orbit around it. And you will see that the sun can be way outside the barycenter. You might have intuitively thought the sun's so massive that if it wobbles, it's only a tiny little wobble. But there you are from 1945 out to wherever it was, 1995, the movement of the barycenter. Now, most of that movement is due to Jupiter. And if we only had one planet in our solar system, then this would be what the sun's orbit around the barycenter would look like. It would take 11.8 years, and it would move at about 45 kilometers per hour, which is pretty slow when it comes to measuring speeds relative to the speed of light. Now, imagine we had, I don't know that you can even see this, but imagine we just had the Earth and the sun. Then that says Earth, but this little circle here is the orbit that the sun would make around the barycenter if it was just the Earth and the sun. And our objective is to find Earth-like stars around, Earth-like planets around sun-like stars. And what is the speed of the Earth, or of the sun around the barycenter? It's 9 centimeters per second, or 0.3 kilometers an hour. Now, 9 centimeters a second is probably not even as fast as this. So what we are doing is measuring the velocity of the Doppler shift with precision, with special spectrographs that we can measure speeds of 9 or 10 centimeters per second. In order to do that, we need lots of light. We have 4 8-meter telescopes here that bring all the light into a coude. It's all channeled through and taken through fiber optics into the spectrograph, which is mounted in that tank there in a vacuum. That's the frame of it, and this just gives you the rough optical diagram. It uses a huge Echelle mirror here, a grating rather. It acts as a mirror. It's an Echelle grating at very high order. There it is in its tank there. And it has been achieving 50 centimeters per second stability over a fair time, and certainly is moving towards being able to detect speeds of the order of 10 centimeters per second, which to my mind is an extraordinarily technological advantage, achievement. And when you stop to think about it, in order to make an observation of a star, you have to take out the motion of the Earth around the barycenter. And that's not just a simple elliptical orbit, and the Earth is moving on average at 30 kilometers per second, not 3 or 10 centimeters per second. So we have to know that as well. Okay, the other thing we have to know about the star, we've established its velocity, and because we've got the velocity and we know the mass of the star it's orbiting, we can get the mass of the planet, basically. The other thing we need to get is the diameter of the planet, and we do this by observing transits, 1 part in 10,000 or so, using satellites to do this. Kepler was the first satellite that did this, staring at an area of sky. We now have TESS. Kepler searched a narrow space out to about 200 light years, and TESS is this satellite here, same sort of idea, is observing over the whole sky, or much more of the sky, only out to 200 light years or so. And this is going to be succeeded by ESA's Plato mission, and this mission has a whole series of cameras that look at different bits of the sky, and it is going to be launched hopefully in 2026, and it will image the sky every 25 seconds, except for the central cameras that will image the sky every 2.5 seconds. And over a 2-year period, it will observe about just over 250,000 stars. So the data output of this is going to be extraordinary. And it's not just going to tell us about eclipsing planets, eclipsing stars. It's going to tell us an awful lot about the natural intrinsic variability of stars. Okay, now time for some results. This graph here shows planet mass, and it's on a logarithmic scale up there, and distance from the star on this axis. And so we can put Mercury, Venus, Earth. You see Earth is at 1 astronomical unit and 1 Earth mass, and Mars, and then Jupiter, Saturn, Uranus, and Neptune. So you can see that apart from Jupiter, we're not really able to observe things like our Earth at our distance from the star. And in fact, there is a kind of observational line limit here, coming down here, this yellow line. And if we want to move this down, then we have to get to the 10 centimeters per second domain of velocity to be detecting Earth-like masses. Now, it's quite interesting that despite the observational selection, there are already 3 basic groups of planets there. And you will see that most of the objects we detect have planetary systems with planets inside the orbit of Mercury. And Mercury gets pretty hot, so they have planets much closer to their stars than we do. Now, Didier Queloz, I think, talking to this audience in 2021, attempted to give a statistical analysis of this diagram, and what it said was 1 to 5% of all solar systems have hot Jupiters, 10 to 50% have Jupiters, cold Jupiters, like our Jupiter. 50 to 80% of all solar systems have these things called sub-Neptunes or super-Earths. And so you can immediately see, quite interestingly, that our solar system, I mean, given this is very difficult because you have to allow the observational selection effects, but it looks as though we don't have sub-Neptunes or super-Earths, and we do have we don't have hot Jupiters. So already it looks as though our solar system may not be typical of solar systems in general. Now, the exciting thing is, when you have both a radius and a mass, you can then work out a density. And what you will see here are these curves correspond to different sorts of material: pure iron, rock, water, hydrogen. So this is the relationship between radius and mass that you have for different materials. They're equations of state. When they get massive, the materials compress. That's why they're not straight lines here. And you can see we put the solar system on. There's Earth, nice rocky iron. It's sort of midway between Uranus and Neptune, which have a lot of water, and Saturn and Jupiter, which has a lot of hydrogen. Jupiter has the same composition as the Sun. So, in the background, with quite large error bars, are the subset of exoplanets that we've observed already. Now, we're getting near the James Webb bit here. If we want to detect Earth-like planets, then we stand a much better chance of detecting Earth-like planets around small m dwarfs than we do, this is to scale, a picture of the sun with the Earth to scale than we do. This is just a point to make. And we are looking, we're not, in that diagram we looked at, we were looking at a range of stellar masses. It was just about planets, but we're sampling a range of planets, a range of stars, different stars, down to these M dwarfs. Okay, well, we all remember, well, some of us do, Christmas Day 2021, when the James Webb finally went out into space and landed up at the L2 Lagrangian point, 1 million kilometers or more away, or 1.5 million from the Earth, with its back to the Earth and the Moon, because it was going to work. It works in the far infrared. The best way to understand the Lagrangian point here is that because when you, if there was well, let's assume this was just a solar system and this thing was somewhere here. The further we get from the sun, the longer we take to go around. But if we sit here, we have a little bit of extra gravity from the Earth. So the Earth and the sun pull here, and that enables this thing to go around a bit faster so that it can go around the sun at the same speed, or in the same time. It has to go a bit faster than the Earth. So that's why the Lagrangian point is good. It's stable, it's metastable, and it's a nice long way, so we don't have radiation from the Earth and the Moon. And there it is, the James Webb, with, passively cooled, with its back to the sun, its heat shield, and it naturally cools to about minus 230 degrees or so, and the instrument package and everything is on the cold side, the rest is on the hot side. There are a series of 4 detectors, and they all look in the focal plane at different bits of the focal plane dedicated to them. And each of these instruments here is both an imager and a spectrograph. And the spectrograph is the tool that we want to use, the most important tool. And that brings us to the first object we're going to look at, called WASP-39b. The WASP, I can't remember what it stands for. It's the name of the project that was looking for variability. Not all the variability has been done from space. Some of it can be done from the ground. WASP-39b is going around a star, not much different, a little bit smaller, a little bit cooler than the sun. So I've drawn the star and the planet to scale there. The planet is less massive than Jupiter, but it's bigger than Jupiter. It's probably got an extended atmosphere. So in the diagram here, it sits below the hot Jupiters and above the Neptunes and super-Earths. And in this diagram, it sits way up above the hydrogen line. How can that be? How can its density be less than hydrogen if it's got an extended atmosphere? So it's kind of bigger and more diffuse. So I just want to consider the whole business of eclipsing and what we actually do with the James Webb Telescope. So there's the uneclipsed star, and there is the star with 2% of its light taken away by a planet. And so as the planet moves across the star, we see the light, the white light, the integrated light, this is a measurement of this thing, with the James Webb, drops by about 2%. And that is the beautiful light curve. See the little planet moving across, and it drops by 2%. And from the shape of the light curve, we can work out essentially the diameter of the star, the planet. Now, let us consider this situation, if the planet has an extended atmosphere. Okay, that's the situation. The atmosphere is shown blue there. Now, if there's no absorption in the atmosphere, then the total absorption will be that of the solid planet, 2%. If the atmosphere has molecules that absorb a lot of light, then the little planet will seem to be bigger, and maybe it'll take away 2.3%. So what we want to do is to observe that eclipse, not just in white light, but in different, either through different filters or using a spectrograph and measuring different pixels and seeing what the brightness looks like. And if you look here, you will see some faint horizontal streaks across here, and these correspond to the wavelengths of certain molecules. So we can take this data in the middle here and bin it all up and display it in wavelength order, and we can get a wonderful spectrum of the star. And now this, if you like, is effective diameter. So when there's a strong absorption band, there's a big peak here, and because the atmosphere is very dark there. And you can see in this particular object, we can see water, sulfur dioxide, carbon dioxide, and carbon monoxide, all well detected. Now, the thing is, the temperature of this thing is 1200, 1200 absolute, so there's no question of life being here, but this does show the technique. And one of the exciting things here is finding sulfur dioxide, which clearly, again, is telling us something about some kind of photochemistry that must be going on, because sulfur dioxide wouldn't just be there in a stable situation. Now, I want to now look at things that are much cooler, these sub-Neptunes and super-Earths. And this is where we come to the work of Madhu Sudan at the Institute of Astronomy, who considered these objects and realized that within a limited mass and radius range, there was a possible structure totally unlike the Earth, but of a water-covered planet with a low-density extended atmosphere. And this was the model, just right for life. So there's the ocean. This is ice, just hotter, of course, but it's the pressure that's turned it into ice, and a rocky core and maybe an iron core, and this outer atmosphere. So there would be a liquid surface here. This surface would be too hot, and so would this one here. So he hypothesized there was an object, or a class of objects, that had extended atmospheres that would be suitable for observing with the James Webb, that had liquid water possibly, and extended low molecular weight atmospheres, and he called them Hycean worlds. Had me reaching for my Greek mythology, wondering who Hyceia was, you know, the goddess of something or other. But it turns out, as he said, all you do is take HY from hydrogen and the last three letters of ocean and stick them together, and you've got Hycean. So that's the origin of Hycean worlds. Now, before I proceed, I just want to give you an idea as to just how complex this business of modeling atmospheres is. So let's just look over here. This is our exoplanet, and we, of course, are observing it when it's in front of its star. So we are looking through this edge of the atmosphere. The star's over there. See all the lights coming? It's bright there. And the chances are that these planets that are close in are now tidally locked, which means they're not really rotating on their axes, so they've got one face pointing permanently towards their star. We are looking through the terminator here between the hot side and the cold side, and we anticipate, well, we see something like this with Venus, in fact, which has very strong winds on it. There'd be strong winds going. So we've got to model the atmospheric structure here. What do we have to model? Well, it's like the Earth's atmosphere. We have to model how the temperature varies, how the pressure varies, and so on and so forth through the atmosphere. We have to take in the chemical interactions, all these mixings, chemical equilibria, and we don't have that data for all the possible molecules and we have to think of all the other things that might be going on in the atmosphere. Thermal inversions, one of the crucial observations we will come to is the fact that he is hypothesizing an ocean and we see no water vapor in the spectrum. So how can we have so much water and no water vapor in the spectrum? Because it's frozen out at a certain altitude, too low for us to observe. And so you not only have to model the structure, but you have to model all the possible molecules. And there are just some of the familiar organic molecules. And then these are the 3 different detectors of the James Webb. So we have to join them together, no easy task, working out from 1 to 10 microns and then even further off. So anyway, having said all that, let us now come to K2-18b. So there it is to scale, and a star less luminous than the Sun. The planet's about 2.5 times as big as the Earth and 9 times as massive. So it's not like the Earth at all. It has, there it is, it has a density closer to that of water. I mean, there is a fair error bar here, but it's not like the Earth in terms of composition. So here we are looking at candidates for life that are unlike the Earth. This is just the same thing on a more refined diagram. It's exactly the same diagram as we looked at before. So what did they get? So here came the spectrum, and here came the identifications. And this was back in October 2023. And there was a lot of excitement because, okay, we've got methane, carbon dioxide, and we've got this stuff called DMS, dimethyl sulfide. Now, to be fair, Madhu Sudan said there was a possibility of there being dimethyl sulfide here. He didn't say it was a conclusive. It was at the 2 sigma level, the possibility of dimethyl sulfide. He also pointed out there was no ammonia, and no ammonia speaks of the fact that the ammonia would dissolve in liquid water. So this all looked as though it well reflected the structure he suggested, a planet covered in water at about a temperature. And if we had dimethyl sulfide, then perhaps we know dimethyl sulfide is produced on Earth by marine phytoplankton. It's the most abundant sulfur compound released into the Earth's atmosphere, and it oxidizes and turns into sulfuric acid. It's very important in weather systems and so on and so forth. So there was a good deal of excitement. Now, almost immediately, 2 other papers were published criticizing this result, coming up with what they considered to be alternatives that were not like that did not have the kind of conditions that would sustain life. So the next year, they spent not reducing any more of their data because they had a lot of James Webb time. They spent it working on these criticisms, and by September and October 2024, it seemed that they had successfully showed that their result was stable and plausible, and so the criticisms were not appropriate. So everything moves on, and that was October 24. April 25, they got more spectra at longer wavelength. Here we are out to 12 microns, that's the original spectra. And they not only found what they thought was dimethyl sulfide, but they found dimethyl disulfide, I think it is. Yes, dimethyl disulfide. And so at a 3 sigma level, much excitement. So it looked like we were back on track again. But, and there we are. Don't quite know why I've showed that at the same time, just gone back to, oh yes, just showing the one spectrum. But, and to be fair, this is something they pointed out, of all these pixels, all these individual measurements and the black stuff, and you can see there are large errors on this, there are 1, 2, 3, 4 pixels or spectral features that are particularly sensitive to the presence of dimethyl sulfide. In fact, they are better explained if we have DMS in the spectrum. There's one blue pixel that is worse explained if we have DMS in the spectrum. And you can see that most of the other, this is a measure of significance, most of the other pixels are pretty neutral. So that's kind of not a very happy situation to be in. So comes this, and the dating is a little bit difficult because preprints come out and then publications. So I'm talking about August 25, and then we're going to go back to July 25. But this abstract was around of this paper. This paper was extremely critical, said there was really no evidence for any biotic chemistry there, and so that was a bit of a downer. But then came this paper published in July 25, in which Madhusudan was a co-author and the rest of the team, and they then did a full analysis, and unfortunately their further analysis suggested that the evidence for dimethyl sulfide was back at maybe the 2 sigma level, and in fact it probably, leaving it out altogether didn't really make a significant difference. So we're back to a sort of somewhat damped down situation. Haven't completely eliminated the property. Oh, and the other thing, not surprisingly perhaps, somebody came up, and it's mentioned in this paper, with a possible abiotic, that means not requiring life, method for making dimethyl sulfide. Now, there are quite a lot of, well, there are 4 or 5 other of these Hycean worlds around. I was only going to briefly mention this one because we're coming to the end. This is a 2-planet system, and this is the white light curve, and it's quite fun. You see, first of all, B crosses, and we have a small dip, and then D comes on, and we have D and B together, and then just D, and D is the one that is the possible Hycean world, and so D's spectrum looks like this, and it does have, maybe it's a better signal to noise, a carbon disulfide, potentially a biosignature, but it does have abiotic origins as well. So, you know, this is the state of play. So I just want to end up with a few observations. There are some gases that clearly go with life, like water, carbon dioxide, ammonia, methane, and are all kind of life-related, but they also have natural abiotic origins. And so there are not so many, or rather exotic molecules that probably or possibly have no natural abiotic source, but do have a biotic origin. And then, of course, something that's come into play is the idea of technological gases. Things like CFCs, gases that do not occur in nature that have been made by technology. And people suggest that might be one way of finding some technologically advanced civilization by considering technological gases. Okay, if we're to make any progress, we need to observe individual planets. There are basically 2 ways we're going to do that. One is by this proposed interferometer array. Actually, I'm not sure it is still viable. It's a huge interferometer in space, optical interferometer that will develop a very large diameter and therefore be able to resolve planetary systems and observe individual spectra of individual planets. The other way is the Habitable Worlds Observatory, and we still don't know what form that will take, whether it'll be like a massive James Webb or it'll be more like a massive Hubble Space Telescope, monolithic sort of thing. But the idea here is sounds quite kind of science fiction-y, but you make this sunshade, which is about 34 meters in diameter, that has these spikes around it that suppress the inner diffraction image of the star, suppress that, and it sits 37,000 kilometers in front of the telescope, blocks out the light of the star, and allows you to see the planets orbiting the star. And, you know, there are serious papers about positioning this thing with respect to the object in orbit. So these are proposals for the future, but things are still quite difficult. This is the reflection spectrum of, it's called modern Earth, it's today. The key things we need to see if we're looking at an Earth-like planet are marked in blue, traces of life, they're ozone and oxygen. And you can see they're quite small dips. And this is a funny-looking spectrum because what it is, it's the ratio between the brightness of the Earth and the brightness of the star. So at these wavelengths here, 10 to the minus 12, that is the brightness of the Earth compared with the sun. 10 to the minus 12, the brightness. In the far infrared, where the sun is not emitting so much flux, we get as good as 10 to the minus 6, a millionth. So that is technologically a real challenge. Okay, the sunshade may help us. And not only there, we've got a lovely spectrum, but look, the features that tell us about life are pretty subtle. That is a transmission spectrum, and the Earth's atmosphere is pretty thin. These are, well, I call it reflection or emission, because reflection at optical, if you're looking at the flux from the Earth, you can say it's reflected light at visible wavelengths. Going into the infrared, the flux is emitted light, radiation, not reflected. And again, these are Venus and Mars, and again, the effects we're looking for are pretty subtle. The oxygen there, pretty subtle, NO2. And you can see superficially the Earth and Venus look rather similar, and that's because of the carbon dioxide. But the clue to life are the oxygen. And one last very sobering view is to look at the signature of life on Earth over time. This goes back to the era before there was any life on Earth, when it was, you know, when it had newly formed. It's got lots of carbon dioxide bands there, some weak methane. This is, you know, this is theoretically calculated. So let us now go towards the end of the era of single-celled organisms, when oxygen was building up in the Earth's atmosphere. There is oxygen, nice strong methane bands that have appeared that weren't here before. But, you know, where does the methane come from? Okay, we think it would come from organisms here, but it could be abiotic. And then, if we go from that era to the present era, today with multicelled organisms, okay, the short wavelength looks almost identical to the pre-life image, the prebiotic spectrum there, and the longer wavelength, okay, we've got a great big oxygen bump and a rather tiny methane bump. So you can see that it is going to be very, very challenging. But let us be optimistic. We are in a new era where we are able to start observing the atmospheres of some of the planets around us, and I think that's quite exciting. And so at that point, I will stop. Thank you for listening.
Well, that was a fantastic tour of the search for life. Are there some questions in the audience? One at the back there, John. Right at the back. That? I'll just say I'm just constantly amazed by the technological advances. Remember,
Yeah.
all of these exoplanet studies, how old are they?
Well,
20 years?
20 years, yes,
Yeah.
essentially.
We've made such progress.
Yeah, thank you very much indeed for the talk. It was very exciting and enjoyable. Given that there were some near misses, and it looked as though life might be on one of those planets, they are a very long way away, and they are very ancient worlds. Could you tell from what you saw or would you gamble or speculate as to whether any of them were in a precursor state for life? In other words, and is there enough time, and will over time the change in what you can see from those planets give you an indication of whether they're likely to be precursors to life?
The real problem is the timescales are so long that we're not going to observe any change. So we just have to statistically hope that we observe different systems in different ages. Now, you're quite right. The planets that are orbiting the cool M dwarfs could well be a lot older than the sun and the solar system. Because we're not really finding much evidence for life, I haven't sort of looked. I could try and plot planet age against something or other, but I haven't done that. But yes, so that was why there was quite a lot of excitement when this recent comet 31 Atlas came through the solar system, because it came from a solar system, we believe, that is several billion years older than the Earth. So in a sense, by the gases that came from it, it gave us a chance to sample composition. But we're not looking for evidence for life there or anything. So yes, I'm not even going to speculate, because I'll let Madhu Sudan speculate, and he's still, hopefully, that we might be seeing signatures for life.
Thank you for your very interesting talk. I just wondered, so you mentioned that atmospheric molecules may be biotic or abiotic, or a mixture, or we might be unsure. What sort of atmospheric molecular signature would be needed to convince us that there is life on an exoplanet? So on a more general level, almost philosophical level, what sort of criteria or threshold should be set for such a question? And then on an observational level, what sort of molecular signature would convince us of that?
Let me just see if I could get back to that one slide. I mean, the problem is, of course, that this is all premised, and it's the best we can do, that life will be in some ways similar to our own. And of course, we know that chemistry is universal throughout the universe. So it's very likely that carbon, maybe possibly silicon at lower temperatures, will be involved. So, I mean, our present, guesses for life is methane, methanol, oxygen, and the problem with oxygen is that, as we know, the early Earth, there was no oxygen. The oxygen came along later. So even that, I mean, if we see oxygen, because oxygen is inherently unstable, I guess the things you look at are the molecules that have to be continually regenerated because they're not stable. And that's really the challenge. But these ones with the yes in this column would be, I think, the things that if Madhu Sudan sees these in his spectra, he will get very excited. But nothing is guaranteed here. And, the environments can be so fundamentally different that abiotic mechanisms may appear. In fact, one of the projects he's now involved in is a huge laboratory project to look at a much wider range of possible molecules. I naively thought that all possible molecules had probably already been studied in the lab, but this is far from the case, apparently.
I'd like to ask a question which isn't so much related to life, but you showed the distribution of hot Jupiters and sub-Neptunes. Is this consistent with the idea of a collapse from a protoplanetary disk?
Yes, it is. And one of the things when you're forming a star planetary system and you have a disk, we believe that Jupiter migrated inwards, not as that close to the sun, but it came a lot closer to the inner, to within, say, the current orbit of Mars, and in the process it triggered the formation of the inner planets, and then Jupiter and Saturn move outwards. But they need a disk to exchange angular momentum with. But yes, I was asking that very question at work, and it is quite plausible for these planets to be in this regime. You've got a question there, haven't you?
We've got a couple of questions online. One from Raphael, who's 11 years old. What is the weirdest yet most fascinating exoplanet, in your opinion?
Oh my gosh, that is... well, there is quite a fun one that I didn't show you that we think might be a candidate for life, and it's essentially frozen all over, except the bit that points to its star is unfrozen and seems to have water on it. So how's that for a weird thing?
Does that have a name?
Oh, yes, it does have a name, and I can't tell you what the name is.
No worries.
No, I could find it, but anyway, let's go on.
So from Andrew, you mentioned that certain planets are easier to detect or get signals from than others, but these are not necessarily those where the likelihood of life is highest.
That's true.
Do we know which planets are most likely to host life, and how can we better target the search for planets where life is most likely? I guess partly the answer is to get the spectrographs working.
Get the spectra. I mean, in a kind of very simple-minded way, what we'd like to do is look for Earth-like planets around Sun-like stars, because we know our Earth has life on it. But mustn't get too excited, because most of the time our Earth had these just single-celled organisms. But yeah, so that's what we'd like to do, if that helps. Okay.
Any further questions from the room or online? Okay, well, all that remains is to say thank you to Robin in the traditional way for a fascinating talk.